So I've been building and designing a programming language and compiler for a little while now, just for fun and to learn. And it's gotten to a point where I just want to share what I've learned and what I've been doing with the world. And the best way I know how to do that is to just, yeah, share my work. I really enjoy watching long form content where people, particularly programmers, but any craft I'm interested in, are just working, sharing their work, sharing themselves, and what they've made and what they're learning with others. So that's what I'm going to start doing. This language is it's been a ton of fun to work on. I have really gone from complete beginner noob to, I feel like I know some things now, and it's been a ton of fun. It's probably been a year and a half that I've been working on this. Of course, just spare time. But, I would think that now I could probably re-implement re-implement this in about a month or two, even with the same time commitment, um, which is which is great. That was my goal. I wanted to learn, I wanted to explore, I wanted to create. I feel like I've done all those things and I'm continuing to, and I just want to share some of what I've been doing. So without further ado, just let me get into the project. I have open here uh, the main function, which looks a lot like any compiler's main function. We load some source text from files, and then we start compiling it. I thought I might run the test suite first. There's some unit tests here, but mostly there are sample programs that the test suite will load, compile, run, and assert things about their output, or just that they don't crash, that they don't fail. So we get some noisy warnings here due to a little version mismatch, but mostly we have 29 tests passed, and a number of these tests are actually not counted because they are in this test source directory. So this all counts as one test, but all of these files are programs that compile and run successfully. You can see based on their names, might need to zoom in a little bit later, covering a variety of topics. They're named after the functionality that they intend to cover. It's not the most interesting language in the world. It's a very basic C-based C syntax, sort of imperative, but with some functional aspects language. I have some aspirations for how I want it to feel working in the language, but mostly I just want it to be a little bit sound and useful, and I'd like to be able to solve puzzles or do things in the language. That's sort of the type of milestone I'm looking for. Um, anyway, so those are the tests. I will quickly walk through the stages of the compiler. It's a very standard architecture. As we can see, it's written in Rust and very minimal dependencies. With a project like this, one of the fun things is you get to do everything yourself. You don't have to pull in a library because you're not trying to save time all the time, right? You can explore and learn. So there are a few things like this string interner that I would prefer to have done myself, but that's a little bit annoying in Rust actually to do without using unsafe. So in the interest of not having any of my own unsafe code, I am using the string interner crate, small vec for optimizations, for performance reasons. But yeah, you can see it's very, very minimal. We have logging, we have some colored output. We're using clap to parse command line arguments. So if I pass help to the compiler, um, these are all the options we support. This is the actual output of the compiler, BFL, baby's first language. And then we see some of the options we have. These are all pretty much for debugging the compiler itself, not really intended for a user to have any interest in any of these flags, but they've been really useful for me. Yeah, log. Inkwell is the big one. This is LLVM bindings. It's just a pretty thin Rust wrapper around the C LLVM API. LLVM is the backend. So one of the things, this isn't just an interpreter, the parser, right? This is a full-fledged, compiler chain compiling all the way down to native code, and fast native code too. which is part of my goal, was to, maybe be able to write some quite high level code with like things like array literables and automatically growing collections and struct literals or dictionary literals, things that you would work with in JavaScript or Clojure or Python is a better example, but have it actually compile to something, to exactly what the C would compile to. Very direct, fast machine code, even though we've written in a pretty high level language. I work mostly on applications, so I kind of want to take what I like about systems programming, how, there's no abstractions without seriously considering their cost, and do an applications programming language, but still that honors those principles so that my web server is using 50 megs of memory instead of 6 gigs, through no particular fault of the programmer. That's kind of the vision, something that compiles fast and is expressive but isn't wasteful. Yeah, so we load the source files and we do some lexing. I think we have an enum token kind. Yeah, so this looks like every other compiler in the world. Okay, I just recorded the rest of this video for about 30 minutes without capturing audio. So let's go through this, but with a little bit of haste. So we have our token kind enum, which looks just about like any other token kind enum in a compiler. We're just trying to go from a raw string of characters to a string of tokens that makes sense. So, we're grouping keywords together. We have an identifier and a string token kind separate from each other. We have character literals, / line comment. We have all of our punctuation type tokens that can have different meanings in different contexts. Again, we're not talking about the meaning, just the character, because in the parser, we're going to assign meaning to these characters. For instance, this bang can mean optional unwrap, and then it can also mean Boolean negation, depending on where it appears. Single quote, double quote for literals, and then we have infix, some binary ops, and that's it. Our loop, our lexer loops, we eat tokens. Yeah, the job of eat token is to produce one token, and it operates on an iterator. So, self is basically just an iterator here. So it makes some progress and it yields a token. We keep going till we yield the EOF token, or till we yield none, and then we produce an EOF token from there. So, a bit messy here, a bit more mutable, kind of funky state than I'd like, but, it's really not too bad. Just a simple lexer. Rule-based, depending on what we see, we parse the next thing. We maintain a little buffer. If we're in the middle of a string literal or in the middle of an identifier, we push to the buffer every character in there, and then when we see the end, either a space or another symbol or the closing quote, then we look at what's in that buffer. That becomes part of our next token. The token that we yield is pretty simple. It just has that kind and then a span. So start offset, end offset, and then the kind, and that's all we actually really need at this stage. Later on, we're going to look more closely. We're going to need more than a span, because if you have a string with a bunch of UTF-8 escape sequences in there, then that can't be what actually goes into your binary. You need to actually embed those actual byte sequences in the binary. So we can't get by with just a span later, once we're really handling string literals. But at this phase, since we're just lexing, that's exactly what we want. And then we get to the typer. Well, we don't at all. We have a lexer, and then we get to the parser. So let me open that up. And the parser operates on those tokens and then produces a tree. It is a syntax tree. We're just boxing expressions inside of other expressions, and so that ends up being an actual pointer in memory. I would like for these to be expression IDs and referenced by index, to avoid the boxing. Not like for a performance thing, but just because it's nice to work with. It makes copies really lightweight and just feels better in general. But we have a tree, an old school computer sciencey tree for now, rather than a flat vector of AST nodes. The best thing to do, we can look at block statement for sure. There's really only 4 kinds of statements. We have a variable definition, val x equal 42, equivalent here. Now we could reassign x. That's an example here. And a lone expression would just be if we just said 42, right? That's perfectly valid. Why would you ever just have an expression? Well, maybe you're calling print line, right? That's why you would have a lone expression, right, as in a statement position. And then we have while statements, while loops that look exactly how you would expect. Let's jump into that. Have a condition, which is an expression. This one isn't boxed. It doesn't have to be boxed because this is a statement. There's an expression, so it's not directly recursive, but it probably should be. Points to a block. That's the code inside the while, and then a span. And then a little note about maybe we don't need the span here because it's in the block and it's in the expression. So there you go. Here's if. You have a conditional expression, you have a consequent expression, you have an alternate expression. Now, nothing in here requires that the conditional is a Boolean, right? It does need to be a Boolean or an optional. We allow Booleans or optionals, but nothing in here says, you know, it could be anything. It could just be the literal 42. We don't care about the validity of the syntax tree here or the validity of the program. It's just a syntax tree. So expression doesn't know what type it is. It just knows what you typed. That worked out kind of nice. And then in the type checking phase, we're going to go from what you typed to actually what type it is. Make sure that it makes sense. Make sure the types line up, all that stuff. So that gets us into the type checker, which operates on an AST module, which is what was produced by the previous step. Basically just a list of definitions, a pointer to our source for source information later, especially for debug info. You can have a function, you can have a constant, you can have a type def, you can have a namespace. Everything pretty much happens inside function. Specifically inside the block of a function is where all the interesting stuff happens because that's where we can have expressions. All right, into the type checker. What do we do? This is heavily inspired by Yacht, the project, the Serenity OS project, the language that Jonathan Turner and Andres Kling worked on for a little while. They don't seem to be working on so much right now, but I find the source code really readable and really nice, and it's been a great learning project for me as an example. So, this is my typed module. I'm just building up, these vectors of variables, types, constants, and functions, and namespaces. So when I parse a new namespace, I push it into namespaces, and then I get a namespace ID. I refer to that namespace by its ID. I put things in it. It's a really nice way to work, at least to architect a type checker. I've been able to do everything I want to do. I think let's just trace. We already looked at if, so we looked at parsing if. Let's look at type checking if. We didn't quite look at parsing if, so parse if. Beautiful. Okay, so everything in parse sort of just takes self and then returns a parse result of an expression. It's an option here because if this isn't an if expr, we don't want to fail. We want to succeed and just say, hey, it wasn't this case, so that we can fall back to the next case. That's how a parser works. It checks the cases in sort of a priority order. So for parsing an if expression in our language, we check if it's keyword if, what if it's not keyword if? Okay, so this is, poorly written. You don't really want the whole thing indented by one level here. I would definitely let else this, not poorly written, but, it's really nice to deal with your cases you don't want to deal with early, return from them like guard style, and not have all your code be indented. You're sort of carrying the mental burden of everything that could have happened above every time you indent, right? So, I understand the pure functional crowd really against early returns because, we've destroyed the locality of reasoning and stuff, but I just don't buy it. I think dealing with a case like this and then just being able to move on, and now we have a binding here. I think that's the key too. We have if keyword, so this line does work. It produces a binding that we need to do the rest of the work. So you couldn't change the order of these and have it still work. So the early return, I don't know. I like it. I think it's really nice. So anyway, we've de-indented this whole function. If it's not an if, we don't do anything. We're essentially just, Well, we're checking if there's an identifier here because we do binding ifs. I'll just go ahead and show you what this looks like. It's how Zig's ifs work. You can pass an optional to the if condition, and if it has a value, then inside your then block, the value inside the optional is bound to this identifier. So that's this looking for the pipe character, the optional ident. But if there's not, well, we're just going to parse the consequent expression. If there's an else keyword, then we're going to parse the alternate expression. And then we're going to build our result. We're going to build a span that starts at the keyword and ends at the very end by extending the span of the if keyword to the end. And then we're going to produce an if expr struct, which just has all the things in it that we just found. We're going to return success. And yes, this was an if expr. Here it is. There we go. Let's type check this. Everything in here is called eval instead of type check or just type. Maybe we could just call it type if expr. All right. What do we have here? So in the type checker, it's a bit different than the parser where, well, we do take mute self, but really that's only just so that we can like increment an iterator position, you know, through our token stream. In the type checker, we really do add things to this self construct. We're adding types to the types array. We're adding functions. We're adding variables and putting them in the pool. You know, we're doing all sorts of things. So we're taking in an expression. This is the if expr we just built in the parser. And then we're going to produce this typed expr, but we're also going to have some side effects. You know, we might be putting things into these contexts. We need to know the scope that we are in. And so the first thing we do is we evaluate the condition. Actually, we do allow optionals. So we call eval expr, and this is the recursive nature of this whole thing, right? Yeah. And then now we know the type of the condition. We can check it. We allow booleans and we allow optionals. If the user supplied a binding, then we allow optionals. Otherwise, we say, hey, you got to supply a binding if you're going to pass an optional to an if. We do this by looking up the type of the condition expression we just evaluated and then matching on it. Here's our type system. You can pause the video. Da-da-da. Okay. And so this entire if is when we're doing binding. Here's some binding stuff. We make sure they passed one. We already checked this. We create a variable. We add that. We get a variable ID, and we are putting that variable in the scope of the consequent block so that when we evaluate that block, this identifier actually points to a real variable. We're also creating an expression, optional unwrap expression that points to the value of that variable so that we can code gen it. Code gen knows nothing about this magical binding if. Code gen sees a much simpler if construct. So that's past the binding part. Now let's just get to like the more basics of the if. So we evaluated the condition. We evaluate the consequent expression. We transform it to a block so that we have a block on both sides. If you pass just an expression to the if, we sort of lift it into a block with one expression in it for simplicity in code gen again. If there's no alternate block, then we make it as if they did an else with just a unit inside. Again, simplifying, reducing the number of cases by the time we get to code gen. We create a scope for the alternate block. We evaluate the expression that the user provided if they did any. Otherwise, this is the empty block we create. We don't do a lot of like synthesizing AST nodes, but oh no, this isn't an AST node. This is a typed node, so this is valid. So we synthesize a typed block here. The overall type, assuming that the type of the consequent and the alternate, the then branch and the else branch, are compatible with each other, then we say that the entire type of the if expression is the type of the consequent. We put that in here. So now anyone who consumes this doesn't need to look at what types these things are. You know, we sort of cache, we provide the overall type of everything in this whole typed module first class. It's already pre-computed. There's no calculation needed to find out the type of any expression from here. That's part of the whole point of what we're doing. We're making sure it's valid and we're finding out the types. So that's typed expr. When we go to Cogin this, if, what we have is an IR builder, which is a little construct that LLVM gives us that lets us say, hey, add a addition instruction, add a branch instruction here, add a this, jump to there and add these instructions. We're just sort of spitting out LLVM IR instructions. So we get in here and we say, okay, what's the machine code type? What's the IR type of the type of this if expression? We set up our blocks, our basic blocks. We don't, you know, this is a single static assignment representation with explicit basic blocks that all have to be terminated. So we have, the way it works is you have an entry block, which is the block you were in when you got to the if. And then the if creates 3 blocks. It creates a consequent block, which is where we're going to go if the expression is true. It creates an alternate block, which is where we're going to go if the expression is false. And then it creates a merge block, which is where both of those branches go to when they're done, that is able to then look up and find out what the result of those expressions were as well. So we create those blocks first, so we have references to them. We're going to need them later. We evaluate the condition, and then we're going to do a branch if equal to, if it's truthy, you know, if it's the same as our Boolean true, we're going to go to the consequent. If not, we're going to go to the alternate. So we build a branch instruction. And now we go to the consequent block and we're going to stamp this out. So we go to the consequent block and then we just say, hey, Cogin the statements in this block. And sometimes it gives none. And that's for early returns, which we don't do anymore. So I think there's a little bit of dead code here, but that's okay. So we'll come down here, you know, we Cogin what's in the consequent, and then we jump to the merge block. And then for the alternate, we do the same thing. We Cogin, well, we go to the alternate block so that the next instructions we emit are actually in there. We Cogin what's in there. And then at the end of that block, we jump to the merge block. Now, well, we branch to the merge block. Now we jump our builder down to the merge block and we're going to put code in there. And the code in there is going to be a fee instruction. And a fee instruction actually is just an instruction that says, based on which branch we just came from, assign a value based on that. So it's kind of like it's if we came from, it's an if we came from expression. So if we came from the consequent block, then we're equal to the consequent expr. If we came from the alternate block, then this fee value is equal to the alternate expr. And that's how we're able to write code like if true 3 else 5 or else 6. The fee says, did we come from here or did we come from here? And then we're able to assign a single value to, you know, to the result of this entire if expression. Okay, so a good segue into our prelude. So we're going to start looking at code written in our language. First, we have a bunch of external definitions. These get matched up at link time, and actually currently I have these written in Zig, exported using the C ABI. So we're able to call into any C function from this language. And here we're calling into functions written in Zig that help us do things like reading a file to a string. And then we have some intern functions. So the type checker runs on these. It does everything, but it just, because it's intern, it doesn't expect an implementation. And it actually tries to assign an intrinsic function type to these at compile time based on the name and the type signature. So by the time we get to Cogin, we actually have an enum that says, hey, this is the internal printint function. And then the compiler knows what to do from there. So you don't implement printint in userland. It's a compiler built in, much like plus, like adding 2 numbers. It's just that it happens to be a function instead of like an operator. Okay, we have a little namespace files. This is purely just scoping, putting a function inside a namespace. So we can call this with files : read to string. It just calls our zig function and returns a string with the contents of the file. We have our print bool here. We could actually rewrite this. We could do print if value true, else false, and this would work just fine. Kind of neato. Assert could also be simplified now that we have Boolean negation. Write it like this. I'll probably do a commit applying these cleanups. I didn't realize this till I got in here. We have our character literal and built-in type from integer to integer into string. Print line, which uses that character from integer and to string that we just defined up here. We have to define this above because it's a single pass compiler. So if we did this out of order, we wouldn't know where those symbols come from. Definitely a big to-do there. We have our built-in growable array, which I'm quite proud of. Definitely the most complex thing because it required me to implement these generic types. 5 intern functions here, which is not great. A lot of compiler built-ins going on just because we don't have the userland language, the expressivity, the low-level expressivity in this language to talk about like the pointer to the actual memory here. It's just sort of a black box that you work with. But I do expose these. Well, length and new, we definitely want exposed, but capacity and grow and set length, we really don't want exposed, but they're here so that we can implement push in userland, which is kind of fun. So push of t takes a self that's an array of t and an element of type t. It doesn't return anything. It mutates the array it was given. If the length is currently equal to the capacity, then we're going to call grow on self. Now we're going to assign the element that we previously didn't have room for. And then we're going to set the length explicitly, and that's push. Now we have our string, which is the last thing in here. String is just like array, except it's always characters and it's immutable. There is no pushing. They're just immutable by default. You'd then have like a string buffer or string builder class that is the mutable version that I haven't implemented yet. But maybe you just use array of character. I'm not sure. Probably not. You probably want it to be string because eventually there's a bunch of char set stuff and just different operations that you care more about with strings. Anyway, from characters, length, index of. We could do a find now that returns an optional int, which would be pretty cool. Just give a minute to sort of look at this. This is really simple, kind of ugly code, but decent showcase, I suppose. And then we have a really bad concat that's just 2 loops and doing character by character, making a new array. This should just be a call to memcopy, which we could make an intern, I think. But I haven't thought through like what the types would be, what types it would take. So maybe we would just make this thing intern, but I wanted to implement it in userland. I think it's a nice showcase. It's calling a lot of different functions and, doing assignment. Yeah, there's the prelude. Then I'll close with just Advent of Code Day 1, 2023. Not the most beautiful solution to this problem by any stretch of the imagination, but there's some neat things in here that I'm a little bit proud of. We have a first and a last function on array. This can be definitely moved into the namespace so that these would just be methods. Didn't really have the raw ingredients to do this until now. These return optional t's. Working with optionals is kind of nice because our if understands them, and we have unwrap, we have a few other things. We have a hasValue method that returns a Boolean on our optionals. IsDigit and AsDigit on character. AsDigit gives us back the ASCII code. We have a new line constant because we need one. Okay, so this problem, we're given a file with a number of lines, and our job is to find the first and last digit on each line and then treat those 2 values as a 2-digit number. So this would be the tens place and this would be the ones place. So 61. Then we're going to sum that value from each line. So we read the file to a string and we print the length because we can. And now we're going to create an array of events. Each array in here represents a line, and it's going to have 2 integers in it, representing our first and last. I don't have pairs yet. This could be a tuple. A little bit of state here. This is the only looping mechanism we have, so this is how we loop with just a while and a condition and using a counter variable manually. If the character's code is a new line, then we're going to increment our line by 1 and set first to true. It'd be nice to just chunk the lines first and then iterate over the lines, but this is where we are. If we have a digit and we're first, then we're going to push a new array to our array of arrays. And the element inside there, this is an array literal. We can see the open bracket and close bracket here, is going to be the integer version of that character. Set first to false. Now if we see another character, we're going to push to the array that we already have at line, at the index line in our array called digits. And the element we're going to push is going to be this character C converted to a digit again. Increment I, we're done. We're going to reset I, and now we're going to sum. We're going to take the first and last element of each of our lines, and we're going to treat the first as if it's in the tens place, multiply it by 10, treat the second as if it's in the ones place. So just add it as is, and that'll be our sum, and then we'll sum up those sums. All right. So while I less than length, here's our binding if conditional. If first digits at I, name it first. If last digits at I, name it last. We're going to do this. We do a whole stack thing that understands precedence, so we can do the ambiguous binary operator here. This is going to bind correctly based on the precedence of the multiplication operator, which is really nice. We use a stack to achieve that, the stack-based approach. Yeah, let's run it. So we'll call go run the compiler, which will build the program. And this is AOC1 NX. And that puts a file called AOC1 NX.out in the NX out dir. So now we'll run it. We'll see the file was 21568 characters long and that the sum is 57346. That is the correct answer to my input, thankfully, for this year. So that's currently kind of where the language is. I'm excited to add a lot more features. Thanks for watching. If you're, of course, more advanced than me, then this is probably pretty unnecessary. You probably know all of this, but if you're newer to compiler development like me, hopefully you found this really helpful intro and will be able to sort of watch some of the other videos where I work more deep dive on a feature and have some nice context available to understand the bigger picture. Thanks for watching.